All right, welcome to the second online lecture. This is going to be on data visualization, and I'm hoping this is going to be a little speedier than the first lecture, lecture 5 on data mining. But if it's not, please again feel free to watch this at a slightly higher speed on YouTube. So let's start here with Edward Tuft's 6 Principles of Graphical Integrity. It may seem a little silly, but there are slightly codified rules for how to visualize data, and at least there's a sort of a established best practice in terms of mostly what not to do. And so let's go through these quickly. The first is that the representation of numbers as physically measured on the surface of the graphic itself should be directly proportional to the numerical quantities represented. So that probably seems obvious, but we're going to go through some examples where this doesn't happen, and it can be very misleading to the person looking at the data visualization. Number 2, and this is a big one for our class. From my perspective as a grader, and this is something that doesn't get often followed in academia, period. If you're looking through peer-reviewed journals, it's pretty bad. Clear, detailed, and thorough labeling should be used to defeat graphical distortion and ambiguity. Number 3, showed a data variation, not design variation. And we'll look at some examples of this. Number 4, any sort of financial or economic time series, when you're looking especially at commodity prices, should be used in real inflation-adjusted units of measure instead of nominal units, and we'll go through that. If you've never heard of inflation, I'll talk about that briefly. Number 5, this is another one that seems intuitive, but isn't always. The number of information-carrying variable dimensions depicted should not exceed the number of dimensions in the data. That means you don't want to use some sort of image with 2 dimensions, so area, to describe, the size of a circle, the area of a circle, the area of some sort of rectangle, to describe a variable that you're measuring in only 1 dimension. And I'll go through why that's misleading as well. And then number 6, graphics must not quote data out of context. So let's go through these 6 rules in some detail. The first one, the representation of numbers as physically measured on the surface of the graphic should be directly proportional to the numerical quantities represented. So this brings up this issue of what a lie factor is. And so the lie factor is used to describe the relation between the size of the effect shown in the graphic and the actual size of the effect shown in the data. And so you're literally measuring the graphical representation of the data, and you're dividing that by the size of the effect in the data itself. And if this is, a very large number, that means you're overstating the size of the effect shown in the data. So the best practice is to keep this lie factor, this ratio, between 0.95 and 1.05, which means you're saying that you can sort of mislead the reader by about 5%. But if this factor is much larger than 1, for example, that would suggest that the graphic is overstating or overemphasizing the actual nature or size of the effect. If it's significantly less than 1, then the graphic is minimizing the actual effect shown in the data or understating it. So here's a pretty famous example. Actually, it's pretty interesting. A lot of the Edward Tufte wrote a book on graphical integrity in data visualization, and a lot of the examples of really bad data visualization come from the federal government, the U.S. federal government. So a lot of these that we're going to go through are older graphics that were put together by different departments in the government. So this was originally published by the New York Times. It shows DOT information, and so what this graphic is, it's kind of neat, right? The whole idea is that you're showing on the left-hand side of this graphic, you're going through time. So the furthest part away, towards the horizon is 1978, and as you get closer to the foreground of the image, you're going through time. You end up in 1985. This is supposed to show increasing fuel economy standards for automobiles. So on the right-hand side, you see these numbers increasing. That's just the increasing miles per gallon. Now, the graphical measurement of the data is a little misleading, because what they're basically suggesting is that the length of the horizontal line associated with each year, it should be proportional to the number on the right hand side. So what this is sort of suggesting is that because the line, the data really suggests that going from 18 miles per gallon to 27.5 miles per gallon is a substantial increase in fuel efficiency. But it's much smaller than the increase shown by the difference in size of these horizontal lines going from 1978 to 1985. The image itself suggests that cars are significantly much more significantly fuel efficient today in 1985 than they were in 1978. And the data actually suggests that while there was an increase in efficiency, it wasn't quite as big. So this sort of illustrates that. If you wanted to, in a simple, very straightforward way, although less creative graphically, show the increase in fuel economy standards from 1978 to 1985, you would just draw a bar graph as shown in the bottom, right? This is the easiest way to show this data, and you can see that the efficiency of cars increases, but it leaves you with a much different visual impression than the top figure, which suggests that fuel efficiency is increased by 5 or 6 times. So number 2 on Edward Tuft's list is clear, detailed, and thorough labeling should be used to defeat graphical distortion. You should write out explanations of the data on the graphic itself. Now this one this is federal data. I think this is mine employment for the United States or some part of the United States. And so the bar graphs, so this is showing operating revenues on the left-hand side, net income or losses on the inside, and then exploration and development expenditures on the right-hand side. Each one of those sections has 5 different bars from 1970 to 1974, but it's pretty unclear what's on the y-axis. You can sort of see in general things sort of at least for the first 2 sections, things are increasing. The last section they decline and then they go back up. But you have to look really closely to see what that y-axis is. And the y-axes are not consistent from one section to the next. And the problem there is that we actually see a net income loss in the second section because the number is written in parentheses, which is sort of a financial or accounting shorthand for representing a loss. Instead of a negative, you have it in parentheses. But that's really hard to keep track of here. And just visually, right off the bat, you have no impression that anybody's experiencing a loss, especially because that value, relative to values in the first and the third section, are actually higher. That bar is higher. So this is terribly misleading. So the third rule is show data variation, not design variation. And so this is an example where you're in the middle of sort of a bar graph. you're zooming in on one particular year. So the first half of the bar graph, you're going from 1973 to 1978, and then you're highlighting or zooming in on variation within 1979, and this is generally considered to be, bad practice. So number 4, in-time series displays of money, deflated and standardized units of monetary measurement are nearly always better than nominal units. So when we're talking about prices, right? Prices for anything, whether it's fuel, electricity, whatever you want to talk about with respect to the energy industry. If we go back far enough in time, then we really have to start thinking about whether we're displaying prices in terms of inflation adjusted or real units as opposed to nominal units. So inflation, is a concept that I think would come up if you took any sort of business or econ class. But in case you haven't, we'll go through it really quickly here. Inflation is a sustained increase in the general price of goods and services over a period of time. There's a lot of different things that cause inflation. When the general price level rises, each unit of currency then buys fewer goods and services. And so what inflation reflects is that the same unit of currency, the same dollar, physical dollar, experiences a reduction in actual value or purchasing power over time as the value or the cost of different goods and services increase. So here's an example of that. In blue, we see the price of some type of coal in dollars per million BTUs, British thermal units. And so that's a typical unit to express fuel prices in, because it allows you to compare fuel prices across different types of fuels. So you could put the price of oil, gas, and coal all in dollars per million BTUs. And in blue we see what the nominal price is. So that reflects what, if you are actually living in those years, and you're running a coal plant, what you would have given someone else for a ton of, or a million BTUs of coal. So in 1949 to 1973, the price changes very little. It stays at, it looks like 25 cents or maybe a little below per million BTU, and then it increases. Now, that gives the impression that if you're comparing coal prices from 1949 to, say, 2003, that prices in 2003 are, about 1.5 divided by 0.25, so about 6 times as high, right? So just looking at the blue line, it looks like coal prices in the early 2000s were about 6 times as high as they were in 1949. Now, the reality is that a dollar buys you less in 2003, significantly less than it bought you in 1949, and we have to adjust for that. And so if we do that, if we adjust for inflation when we're talking about these prices, we get this pink line, the real inflation-adjusted price of coal throughout time. And so what this shows is that relative to 2003, coal prices in from 1940 to 1970 were about the same as they were in the early 2000s. So it makes a big difference in how we represent this price data. Makes a big visual difference in how we perceive the price to have changed over time. So number 5, the number of information-carrying variable dimensions depicted should not exceed the number of dimensions in the data. So this is what I was referring to when I was saying you don't want to use some sort of object, that two-dimensional object, like the size of a circle or a rectangle, to represent one dimension of data. And so here's an example. At the right here, you see what's meant to be a measure of the purchasing power of $1. So a relevant example to what we were just talking about. So the length of each dollar bill here is what's supposed to be measured here. So you can see at the bottom of each dollar bill they have a year and then the purchasing power of a dollar, and they're starting in 1958, and they're saying, in 1958 the purchasing power of a dollar was in 1958 dollars was a dollar, and so as inflation increases through the future, the purchasing power of the dollar declines, and you can see that in the subsequent years, so 1963, 1968, 1973, etc., the purchasing power of the dollar declines because of inflation. And what they mean to do is show that the length of the dollar bill is what is proportional to the decrease in purchasing power. So the John F. Kennedy dollar is 94% as long as the Eisenhower dollar, and the Jimmy Carter dollar is 44% as long as the Eisenhower dollar. The problem is that it really doesn't look like that. The Jimmy Carter dollar doesn't look like it's 44% as big as the Eisenhower dollar, because when you assess this in terms of its area, it's not. It looks like it's about a quarter as big. Even though the length of the dollar might be 44% as long as the Eisenhower dollar. So it really gives this impression that the value of a dollar, even though it says 44 cents, the visual impression is that the Jimmy Carter dollar, or in 1978, a dollar is worth much less than 44 cents. It looks like it's worth about, a quarter, or maybe even less than that. So the last, graphical integrity principle, number 6, is that graphics must not quote data out of context. And mostly what this means is scale. The top figure here shows this really steep decline from the 4th to the 5th data point. And it's all a matter of perspective, right? If you start the figure the lowest possible value at 450 and it goes up to 500, yes, this looks like a really steep decline. But if you start the figure at 0 and go up to 500 and you sort of zoom out, then you can see that what looks like a really steep one-year decline is really not that big a deal. And so most of this not quoting data out of context has to do with scaling issues on axes. And this can be sort of a nefarious practice, especially in science or academic research, or industry research as well, for that matter. Like if you can sort of make results look more significant or less significant than they are by manipulating the scale. And so it's always important as a designer of graphics to be aware of that, but also as an interpreter and a consumer of this information, you have to be aware that people may be trying to do this as well. So this is a funny example of what I think is a pretty bad graphic, or one that uses data out of context. That was in an article on Bloomberg that I read a couple months ago. And the article was about how farmers are taking on increasing amounts of debt and are more leveraged financially than they have been in a really long time. And a big part of that has been really low interest rates. So it's just cheaper for people to borrow money now, and as a result, farmers are borrowing more money to do a variety of different things. And the article was sort of talking with some concern about this, right? Because if you're increasing your debt burden, that means a lot of your costs are fixed and tied to paying off that debt. And if you have a bad year and you're a farmer, then it puts you in sort of a precarious position. But the title of this graph made me sort of laugh because it's loan costs rising, right? And so this is showing the fact that the Federal Reserve raised interest rates for the first time since 2006. But this gives you some historical context about the significance of the interest rate increase. I mean, we've gone through years not that long ago when interest rates were above 5%. And now we're talking about going from almost zero to just a tiny little uptick, and everybody's sort of worried about this, and I mean with good reason. But I found the title to be quite misleading from the actual data that's being represented. So there's some other, besides those 6 more general Tufte principles. The first is to maximize the data ink ratio. So the amount of ink that you're actually using to display the data over the total ink used in the graphic. When the upshot here is that you just don't want things to be colored in as much if they're not the actual data that you're presenting. So this is suggesting that the graph on the right is preferable to the one on the left because it's not any less visible. Like you can, having those bars, the teal rectangles colored in behind the bar graph on the left is somewhat distracting, and it just doesn't add anything to the figure. So I think this is sort of like addition by subtraction. Simplicity in here is helpful for the viewer. And this is sort of a funny concept as well, avoiding chart junk. And there's lots of really quite interesting examples of this. I actually just was looking online for some information from Duke Energy about their generation mix, and they had just this ridiculous image where it was like their generation mix was like the screen of an iPhone or something like that. I mean, it was just awful. You couldn't tell what was going on. And this is similar, right? You don't want to, it can be fun to try to embed, your data in some sort of cartoon or, more creative graphical context, but it's highly distracting, and really is considered to be a poor practice in the visual representation of data. So obviously here we want to go away from this monster slash dog, I don't know what that is, to something on the right that very clearly lays out the data in an unambiguous, not funny or creative, but very clear way. Here's some more. I actually like these. I mean, there's a really appealing part of chart junk. It's just, you're not supposed to do it. And so here, on the top, they're turning a pie chart into a hemisphere, which is kind of cool. But just show the pie chart. And at the bottom, I also like this one. This is pretty funny as well. But yeah, just show a bar graph. Don't turn them into shells. So on the use of color, Tufte basically says, above all, do no harm. In some cases, color can be something that enhances and makes a graphic clearer or easier to interpret. In other cases, it can do damage and be something that's confusing and just in general not necessary at all. So above all, do no harm with color. And there are specific cases in which color can be more useful. So why use color? Labeling, measuring, imitating reality, so mostly with maps, and enlivening. So this is a really famous graphic that shows the brown. This is the size of Napoleon's army as it marches from west to east towards Moscow. So that's the brown, or tan is the size of the army as it marches to Moscow, and you can see the width of this graphical representation of the size of his army declining as they march to Moscow. and it's punctuated by certain events. And then once they get to Moscow, you can see the return journey in black. And so this is again like a really famous chart, and what's interesting is you can see at the very bottom it tracks the temperature experienced for the return journey, in which a lot of Napoleon's soldiers succumbed to the cold temperatures and died. So this is a famous graph. So measuring can also be used for, or temperatures can also, colors can also be used as a measurement. This is a heat map, and there's all sorts of different ways. Like we could, we've talked a little bit about plotting things in 2 dimensions. Looking at a matrix, right? And so the value of each index, or element in a matrix, could be represented by a color bar, and that's sort of what this shows here. And this is just showing compatibility from OkCupid. Matching up different people, different males on the y-axis, different females on the x-axis. And here, compatibility is a numerical scale. It looks like from 50 to 70, but it's also a color scale. And so let's see who matches up well together. Agnostic people, agnostic females, Jewish males, agnostic males, Jewish females. Who does really not well together? Looks like Muslim males, and pretty much everybody except for Muslim females. And then there's a lot of people sort of in the middle that are yellow and orange. Okay, imitating reality. So, obviously if you're doing mapping, color can be useful to represent different geographical or geological formations, the presence of water, etc. In this case, this looks like a topographical map, maybe, where there's, it looks like there's different shades of colors used to represent depth of water and the height of any sort of geographical relief. Enlivening. This is also a really famous example. This is a version of the Elements of Euclid, the geometry textbook from Oliver Byrne. And the use of color here is, really simple, but, pretty, beautiful at the same time. So this is a really good example of the use of color. So they're not overusing color, they're using it to make things clearer. Okay, so that's all the Edward Tufte stuff we're going to go through, and I know it's a little interesting to know that there are fairly standardized ways of visualizing data, and so as you go through this course, try to the best of your ability to stick to some of those principles, or at least think about them as you're putting things together, in the cases where we do visualize data. Now, there are some common types of data visualization that's used in the energy sector. When we're talking about big data and how that's displayed graphically, there are some different types. The first is hierarchical data, then clustered data, time series data, which is what I encounter mostly, and then high dimensional data. So multivariate data. So here's an example of hierarchical data, not from the energy sector, but imagine if you had, if you were a bookstore, right, and you had a bunch of different books, and you could divide them by genre, so arts and photography, children's books, mystery, nonfiction, magazines, romance, etc. And then each of those genres, in some cases, could be split up into subgenres. So children's books could be baby books, age 3 to 5, which my kids would read, age 6 to 8, preteen and teen, etc. And mystery, there's different kinds. Romance, apparently there's 3 breakup books, 1 makeup book, science fiction and fantasy. And each of those subcategories then is associated with a topic. And then what we're really keeping track of here, the sort of outcome that we want to pay attention to, is how much money is made from each of these topics, subgenres, and genres. So how would we sort of track the revenue through these 3 different categories, where sort of the genre is the parent category, subgenre is the offspring category, and then topic is the offspring category of subgenre. So one way of representing hierarchical data like this is a sunburst plot, and you can do this in Excel. And so here we have closest to the center of the circle all the parent categories, right? The genres. So we have children's books, romance, mystery, magazines, nonfiction, etc. And then the circle immediately outside of that are all the subgenres, right? So each subgenre belongs to a specific genre. And then in the cases where there are more specific topics, and they're not all, all the subgenres don't have specific topics. For example, preteen, baby books, and age 6 to 8, these do not have subtopics, but the ones that do, like age 3 to 5, those subtopics emanate out from the subgenres. And here the outcome that we're tracking, revenue, is then represented. So each the share of this 365-degree angle around the circle is broken up by the share of the total revenue that each genre, subgenre, and topic makes up. So it's a way of representing visually where you're getting most of your revenue and how those sources are broken up into different types of subcategories. An example that we could think of that's similar from the electric power industry is how we think of a really natural hierarchical structure in the electric power industry is how power systems are administered, right? We think of them as mostly being owned and operated by utilities, but there are categories of organizations that are broader than utilities. So if we start way at the top, we have NERC, right? So that's the North American Electric Reliability Corporation. And they oversee basically everything in North America, like the integrity of the grid, making sure systems are interconnected and reliable. And then NERC is divided into 3 subregions. Those subregions in some cases consist of many different independent system operators, or RTOs, so system operators that may be made up of many individual utilities. And so if we're thinking about the West Coast, right, so WECC is the western portion of North America that's involved in NERC. That's made up of BPA, which is the Pacific Northwest, and CAISO, which is the big electricity market in California. There are many different utilities in CAISO, PG&E, Southern California Edison, San Diego Gas and Electric. And if we just look at one of those utilities, then we can explore what types of generation capacity they have. So nuclear, gas, hydro, etc. We could include renewables, and then we could even zero in on gas and look at different types of units, whether it's just a combustion turbine or combined cycle power plant. And then we want to be worried about some sort of ultimately an outcome, right? And that could be emissions or revenues or total generation produced. And so you can sort of think about how, like, we could have a giant sunburst graph where we could look at everything that comes under NERC, every subregion, every ISO, RTO, utility, and then look at eventually emissions from. We could track emissions, through each type of power plant, through each utility, through each region of the country. Now that would be a really giant, pretty much uninterpretable sunburst chart, but you could do this for one utility or maybe for one ISO or RTO to get a visual understanding of where all the generation's coming from or where all the emissions are coming from. We also use cluster data quite a bit, and sometimes this can be object data. I gave one example when we talked about data mining about how I use cluster analysis to reduce the computational burden of some power system models by grouping different power plants functionally together and making them sort of combining them into one part of a model. The example below uses is more spatial temporal clustering data. So this is for the state of Colorado. If you have a bunch of data about the availability of solar production, and you want to cluster individual, spatial areas together based on their what their time series of solar availability looks like throughout the day, you can do this. So this is sort of time series clustering. You want to group. So here on the left-hand side, we have 3 different locations, and each location has sort of a different signal about what solar availability looks like. And you could imagine that if we had a signal like this for a lot of different locations throughout Colorado, we could cluster. We could write an algorithm that groups all the different areas together that have a signal that looks roughly the same, and then we could, classify them or just group them together. And it turns out that if you do this in Colorado, you end up doing sort of a spatial clustering, but it's not, it's not always neat. You can see in the figure on the left that it's very spatially dependent. So the places that have one type of signal tend to be near other places that have the same type of signal. But when you think about how these regions interact, we're not talking about straight lines, right? And there's some messy areas where you have yellow spaced a couple different areas. So we've already talked a little bit about k-means clustering here, and so this would be another example. So if we have data about energy consumption per square foot, and we have that on the y-axis and it's standardized in some way, and then the standardized age of a home on the x-axis, we could try to figure out, we could put these into groups somehow. And so here, the clusters, there's only 2 groups, even though there's a bunch of different colors. But here the clusters are divided into pluses and circles, with the pluses being, in this case, homes that have pretty high energy consumption per square foot, and the circles being homes that have pretty low energy consumption per square foot. And in this case, you can identify some sort of pattern where the older your home is, the more likely you are to be in a house that has high energy consumption per square foot. And utilities might want to do this in order to identify which segment of their residential customers they should target through some sort of efficiency or weatherization program. And in this case, you would target people that have high energy consumption potentially and older homes, right? So that might identify people who probably can't change their behavior that much to alter their energy consumption. It's just a product of them being in a really old house that's not very efficient. Another use or example of the use of clustering in energy data is time series clustering of electricity demand profile. So imagine you're a utility, and instead of building a new peak power plant or buying a really expensive energy storage unit in order to meet electricity demand during peak hours of the summertime, you're interested in starting up a demand response program where you pay customers to reduce their electricity consumption during mid-afternoon when peak demand is the highest. So the challenge for you is to identify which customers you think you should. Imagine you don't want to send out information and spend a lot of money trying to recruit customers if they are not going to either want to help or if they don't actually use electricity demand during that period, right? So you want to go after the customers that do use a lot of electricity in the mid-afternoon during the summer that would be willing to, reduce their consumption for some monetary compensation. And so, imagine if you had some information about everybody's hourly electricity demand profile, during the summertime. You might want to group your entire customer base into categories based on what their hourly electricity demand profile looks like, and then target, one or two, or prioritize those groups in terms of who you should go after to try to engage in this demand response program. And so you could take thousands of individual electricity demand profiles and then group them by similarity into 5 or 6 that look roughly the same. And so that's what's shown here on the right here. So time series data is huge in energy analytics, and that's because energy systems are highly dynamic. They're highly time varying, and so time series analysis is very, very important. So visualization can be useful in showing repeatable patterns or anomalies or extreme events, step changes, so systemic shifts where the future is no longer looks like the past, but also exploring the relationship between two different variables or processes. So at the top here we have, or in both cases here, we have examples of repeatable patterns. The top shows hourly electricity demand in the winter for someplace in the southeast. So each demand, each day, each 24-hour period has 2 peak periods. It looks sort of like 2 camel's humps in the morning and the evening. The demand pattern looks different in the summertime. But this is a highly recognizable pattern. How electricity demand during the day is going to change in the winter is very, very predictable. Same goes when you're thinking about seasonal changes in electricity demand shown at the bottom. This is peak electricity demand on a daily basis, but shown over 10 years. And you can see that there are periods during the year that have very high electricity demand, especially summer, but also winter. And then there are periods that have really low electricity demand. So these troughs are the spring and the fall. When you're thinking about variable renewable energy, and we'll spend a lot of time thinking about this, or at least some time thinking about it later in the semester, time series analysis, again, is very, very important because of how dynamic renewable energy production is. In the case of solar, it can be quite variable. We think of solar as more predictable than wind, but solar production can vary for a variety of reasons throughout the day. But certainly, and so this figure at the right shows many different records of daily solar or hourly solar production overlapping each other in gold, and so the average is this black line. And then you can see wind is all the blue lines, right? So much more variable, so that it's harder to pick out a pattern in the hourly wind production. And then electricity demand are all the pink or magenta lines, with the average again in black. And so, this is sort of exemplifies in some ways the challenges of integrating renewable energy for your utility, because your magenta lines, your electricity demand, are much less uncertain, right? You pretty much know what the general range in which you're going to be. Solar, you have a better idea, and wind is kind of all over the place. Time series visualization can also be useful in recognizing extreme events. This is daily stream flow. I'm not exactly sure from where, but droughts pose extreme risk for electric power utilities. So any period here where you see not much blue it would be a drought, and then really really high blue would be a flood or a flood event, and so that would you have a lot more hydropower production during a flood and a drought. You have way less hydropower production, potentially even issues with thermoelectric power plants because of lack of water availability for cooling. Time series visualization is also useful for identifying step changes, and the most recent really big step change that has occurred in the electric power industry is fracking. This extended period of low natural gas prices. We really are sort of in this different state of the world since 2008, where natural gas prices have been low and much less volatile for an extended period of time. And this has identification of this, not just visually, but has had tremendous consequences in terms of how people are making investments, about what types of plants to build, and how they project things out into the future about the potential for volatile natural gas prices to reoccur. So time series visualization can also be used to show pretty clearly the relationship between different types of variables. So at the top, this shows the relationship between electricity prices and natural gas prices. So this is increasingly the case as we replace coal with natural gas, but in many states for a long time, electricity prices have been primarily driven by natural gas prices. And at the bottom, you can see this sort of zero-sum game taking place where there's a limited amount of market share, right? We have a limited amount of electricity generation that we need, and some proportion of that's going to come from nuclear and hydro, etc. But the two technologies that are really competing at the moment are coal and natural gas. And you can see that pretty clearly here as coal declines, not just over the long term, but over shorter time periods. Natural gas does sort of the mirror image, right? So as coal declines, natural gas increases, and if coal increases over a short period of time, then natural gas tends to decrease. So high-dimensional data, this is a three-dimensional plot of data, so you have two independent variables, an x and y, and one dependent variable. So some function z whose value depends on the value of x and y, and we're exploring what that value of z is over a whole range of x's and a whole range of y's. And here we're also we're not just plotting the value of z on this third vertical axis, we're also coloring it. And so that can be a really nice visual to show high-dimensional data. Here's an example. You have two independent variables, the month of the year and the hour of the day, and then one dependent variable, which is wind energy production. On the vertical axis, the z-axis, and then we're also here coloring wind energy production as well. So as you go higher up on the vertical axis, you go more from these cool blue colors to red and eventually black. And I ask here, is this a good figure? I really don't like this figure. I think it's a little misleading, and so I was hoping you guys would think about why. So another way that we think about visualizing multivariate or higher dimensional data is looking at trade-offs. A lot of times in power systems, you have many objectives, right? You want to maximize reliability, minimize environmental impacts of all different kinds. You want to minimize cost, etc. Or even maximize, if you're thinking about things from the utility standpoint, you want to maximize profits or minimize risk, etc. And so ultimately and inevitably, there are trade-offs, right? You cannot get 100% of your goal in all of these. Although that's the goal, ultimately we want to design power systems that do this. Right now, it's sort of a zero-sum game, and so visualizing trade-offs can be quite useful as well. So one way to do that is to plot. If you did know how your objectives varied with relation to one another. So if you had one objective on the y-axis and one objective on the x-axis, you could plot how those trade off, and this we would sort of describe as a frontier, a trade-off frontier. We'll talk more about this as we get into optimization and stuff like that. In really complex systems, you may have not just two objectives that are trading off, but many, many objectives, so 6 or 7. And then, as you can imagine, visualizing those trade-offs gets pretty complicated. And this is an example of a parallel axis plot where the direction, so you have 6 different objectives here on the x-axis: hydropower revenue, water reliability for a city, some sort of environmental metric, some sort of recreational benefit, water reliability for a nuclear power plant, and then water availability for a coal plant, the Chester coal plant. And so ultimately, the preference of each one of these objectives is to have some sort of score towards the very top of the y-axis. So an ideal situation would be one line going across all 6 objectives at the top. But what we see is that achieving one of these objectives 100% for one, like the environmental index, necessarily means that you're going to reduce the value of the objective for others, right? So an environmental, a really good environmental situation here might mean you're letting a lot of water go from, this is modeling things for the Chesapeake River. In this case, it's saying that if you do the right thing for the environment, that might entail releasing a lot more water from reservoirs to satisfy some sort of aquatic species requirement. And as a result, then there's less water available for, for recreation or for Baltimore, etc. And so the position of the line going across along the y-axis shows you, it gives you an idea of how well you're meeting the objective or the preference of each one of these objectives. And the position of the line on the y-axis is also colored to give a better visual interpretation. Alright, so that's it. Damn, this was another really long one. Almost an hour again. So I think they're going to shorten up. I was a little paranoid I wouldn't have enough to talk to, so I probably overdid this. So hope you guys are all watching this on a faster speed. Alright, that's it. Thanks.